A nuclear power plant's electrical system contains thousands of individual safety circuits. Designing one cooling system control circuit traditionally takes a team of engineers several weeks. One wiring error in a Class 1E safety circuit can trigger a regulatory shutdown costing millions per day. The design bottleneck is real. In 2025, engineers began using Claude differently, not as a chatbot, as a lead design engineer. Feed it the IEEE standard, the component specifications, and the system requirements, and ask it to generate the circuit logic, the netlist, and the validation checklist. Months compressed into days. To understand why this matters, you need to understand what a power plant electrical design actually looks like. A single nuclear plant has over 30,000 individual instruments and control devices, each one connected by circuits that must comply with IEEE Class 1E safety standards: redundant, seismically qualified, and fire protected. The traditional design process uses CAD tools developed decades ago. Engineers manually cross-reference component datasheets, safety standards, and thermal limits for every circuit. A peer review of one safety-critical drawing can take a senior engineer 40 hours. Human error in this process is not a risk. It is a statistical certainty. Step 1. Load the context. Paste the relevant sections of IEEE 603, IEC 61513, and the component datasheets directly into Claude. Its 200,000 token context window holds an entire safety standard and a full component list simultaneously while reasoning across all of it. Step 2. Write the engineering prompt. Not design a circuit, but design a Class 1E passive cooling control circuit for an SMR with N+1 redundancy per IEEE 603 Section 5.1. Identify all single points of failure. Generate a SPICE netlist. Cite the specific IEEE clause for every design decision. Claude's output is immediately useful. It generates a complete circuit description with component ratings, a SPICE netlist ready to simulate, and a point-by-point IEEE compliance table. Each design decision is cited to a specific standard clause. The engineer is not given a result. They are given a documented argument. The same output feeds directly into KiCad. A Python script converts Claude's netlist to a KiCad project file automatically. What would have been 3 weeks of manual drafting becomes an automatically generated starting point that the engineer reviews, refines, and approves. The validation step is where Claude's analytical capacity becomes most powerful. Feed it a completed circuit diagram and ask it to act as an independent reviewer. It cross-references every component against its datasheet, checks every connection against the applicable IEEE clause, and flags every thermal limit and redundancy gap. In testing, Claude identified a thermal limit violation on a relay operating at 94% of its rated capacity, a finding that typically requires a senior engineer's focused review to catch. Traditional peer review of that same circuit, 40 hours. Claude's review, 4 minutes. The case study: a passive cooling control circuit for a 300 megawatt small modular reactor. The original manual design took 6 weeks, 3 engineers, and 47 revision cycles. The function: control the valves and sensors that keep the reactor cool when normal power is lost. The stakes: highest possible. The Claude-assisted design: 3 days, 2 engineers. The AI generated the initial circuit logic, component selection, and IEEE compliance table. The engineers reviewed every decision, caught 2 AI errors, and approved the final design. Speed gain, 10 times. Final IEEE violations, 0. The engineering ethics are non-negotiable. Claude cannot hold a professional engineer license. It cannot stamp a drawing. It cannot be held legally liable if a circuit fails. Every output from Claude must be reviewed, validated, and approved by a licensed engineer who accepts full professional responsibility for the design. The role of the engineer transforms rather than disappears. Instead of spending 80% of their time on manual drafting and cross-referencing, they spend 80% on safety judgment, design philosophy, and regulatory strategy.
Our safety philosophy
Claude handles the
focuses on
tedious.
strategic redundancy,
The engineer handles the
ensuring that the core
consequential.
protection systems remain
This is
robust
engineering
under all
2.0.
conditions.
The future power plant will be designed faster, with fewer errors, by engineers who spend their time on what only humans can do. Claude is not the engineer. It is the most powerful tool the engineer has ever had. Which circuit would you design first? If you found this video useful, subscribe to Future Energy and Technology. We cover every major breakthrough in nuclear, renewables, storage, and the grid as it happens. Hit the bell so you never miss the next one.